and I'll be talking about mixed language development this morning. So roughly the outline for the talk is I'll talk about JNI, and then I'll talk about debugging, and then I'll talk about performance tuning. You may have noticed I've been fussing around with the laptops. My plan was to do my demo off my laptop, but I'm having trouble driving this screen. There doesn't seem to be any resolution that my laptop's happy with and the screen is happy with. So I'll try and swap over towards the end of the talk. So I've got some, live demo stuff that I'll do at the end that I would have done mixed in with the talk. So you have to bear with some of the technical hiccups there. So let's see. Okay, I'm part of the Solaris Studio team. That's the native language development tools, C, C++, and Fortran. And there's a whole bunch of other talks during the week that we're doing, and this is the outline of them. We have another talk at Java 1 doing more depth on performance analysis using Studio. And so with that, I'll head into the talk. So what's the level here? How many folks here use JNI frequently? Okay. Wow, most of you. Okay, so this will probably be bread and butter to you. But let's go over the introduction stuff. So it's Java native interface. So we're going to be two ways of doing this is calling native code from Java, or the other way around, calling Java from native code. I'm going to just do calling native from Java. And so the questions really are, why do we want to do this? Because this is just a bit of a headache, isn't it? So this often comes in from reusing legacy code, like you've already got a library, an application that does what you want, and you don't want to change the code because you know that it works, it's been validated, or you don't have the resources to change the code, even though you'd like to. There's also leveraging hardware features. So as chips develop, they put new instructions in, new features into the hardware. And often the only way of getting access to those features is through some sort of native code stuff, some sort of disassembly. For example, if you're handling the crypto instructions directly rather than going through OpenSSL or something like that, then there's often a reason for doing this. Now, performance, I put lots of question marks after that. I don't think performance is a really strong concern, but sometimes it is possible to write some hand-tuned disassembly, some tuned C code that does do a bit better than Java, but in general, I think you're better off not doing it for that reason. So, the basic thing here is we're going to have a short bit of native code that we're calling from Java, and this is the outline of a example code. So, the important thing here is that the method we're going to call is declared as being a native method. So just the native keyword. And then we're going to load the library. And the important thing here is that it uses the default search path. And it has automatic suffix and prefix. Meaning that why it's important is that on Windows it's going to be called something different from if it's on Solaris or Linux or whatever. And so you don't want to really put that sort of noise into your application. You just want it to work. Obviously, native code does mean that you are platform aware, so it's kind of not that critical because at other points you are going to be dealing with a native environment rather than just sticking in the Java environment. And then finally, you create a new object and you call the method that you want to call that's the native one. So that's pretty straightforward. Then on the other side, you've got to write your library code that handles this method and uses it. So first thing to do is compile your Java application as you get your .class file. And the second thing you're going to do is to generate header files from that. And you can do this manually, but there's an automated process for doing it, so I would use that. And it's just Java H and the class file. And that will produce a .h file corresponding to the the methods that you've got that need to be written. Now you'll see if you look at the .h file, it includes a lot of stuff. But fundamentally, you're going to come down to, let's go to this. It includes a jni.h file. This pulls in all the Java specific defines and so on. And then you've got your native method that you're going to be calling. So you notice it's got lots of decoration there. And we'll talk about some of that. So the first thing to note, as a, if you're looking at this from the native code perspective, the function name is Java, your class, your object, and then your method, all concatenated together. So this is Java hello message. And that's the way that the classes, the methods are named. It's a C calling convention. So it's not got name mangling and stuff like that, which allows you to do C calling and C++ calling. Then you've got your platform-specific declarations. So it's scoped as external, JNI export. So in Windows, this will convert to decl spec export. In other environments, you may actually not need an export because by default they get exported. And then again, there's a calling convention. Some platforms will require a specific sort of calling convention, and others just do the default. So again, these kind of get defined on depending on what the environment you're in is. And then there's a couple of parameters, the Java environment and the object being passed in. So this allows you to access both the environment and the object from within your method. So then the bit you've got to do is write your method. So you just initially start off with whatever was defined in the header file, and then you put your code in. Right. Then you want to compile the native code side. So this kind of looks ugly, which is fair enough. So you've got quite a spectacularly long compile line there. So lowercase g for debug. I'm always, in the studio environment, debug information doesn't have an impact on performance in most cases, so it's just worth doing. O for optimized code, again, -O on most compilers represents a pretty good trade-off between compile time, performance, and so on. So it's always good to throw in -O for anything you're building. And then we're building a library. So in the Unix world, -G for a library, and then -K pick for position independent code. So both of those are kind of required. You can do position independent libraries or position dependent libraries, but generally in Unix you're not recommended. And then you need to find the header files. That's the jni.h file. So that's going to be located in your include directory. And then I'm building on Solaris in this particular instance, so I also need to include the Solaris subdirectory there, which contains the platform-specific defines. So once I've done all that, it should build and run. Okay, so now I've got my, if I had this laptop currently plugged in, I would demonstrate all this. So we're just going to go on and go through some of this later. Okay, so running it. At this point, we've got a class file and libhello.so that we want to use. So we run hello and it fails. And this is something interesting going on here. You can see from the stack, it's complaining about system.loadLibrary and hello.java line 12. And that's the line in my code where I said, load the library up. And so I've obviously got to think about where this library is. So it's not necessarily going to be on the path. So one way of doing it is to specify LD library path to be the current directory. And then run it, and hey, it works. Brilliant. There's only two things wrong with that. The first is I've specified the current directory, and so if I run this from somewhere else, it is no longer going to be found in the current directory, and that could be bad. And the second is that I've used the environment variable LD library path, which is really not what you want to do on production code. You want something a bit more robust. So, yeah, on the linker side, the native language side, we don't like LD library path. It's a bit of a hack. It should be used for testing and debug, but not necessarily on production. So what else can we do? Well, another way of doing it is to define the Java library path on the command line. And this is probably the best way of doing it, really, because it's relatively straightforward to do and doesn't involve any particular platform-specific nastiness. Again, I've used the current directory. I've used dot. That's probably not what I would recommend. I would recommend hard coding it or a script which figures it out. So anyway, this works. There is another way of doing it, which is that I'm going to change the code. And so I can get the user directory, which is basically the directory that you're working from, which again is a bit dubious because you may not be working from the right directory. And then I can append the file name and I can explicitly load the library. And that's a bit horrible, but it does work. So there's multiple ways of locating the library, but the message there is, by default, you may not find it. So what we've got now is we can run the program, and we've got a library that contains all the code we want. Now, that's a good start, but it's not actually doing anything useful. Because at the end of the day, we aren't actually passing any parameters in, we aren't passing any information in, and it's the processing in the library that we're really interested in. So, parameter passing. So, the first thing to do is to define what parameters you're going to pass over. And then you're going to pass them in, you're going to load the library and do some work in the library. So, let's go back. Here we've got the Java code, and you can see that top bit here, if I can, yeah, is that sharp? Not really. Here's the declaration of the function, here's where I'm using it, and here's where I'm loading the library. When I use Java H, I will get a header file, and then I can use that to build the C file. And the C file is going to look kind of like this. So I've got my environment, I've got my object, I've got a Java double array, and I've got a length, an int. So I'm getting passed in everything I need, but they're not necessarily in the right format. So I'm going to have to do some processing to convert from the Java format into the native format in order that I can use these from my native code. So I'm going to use the Java environment. I'm going to ask that to do the processing on my behalf. So I'm going to, first of all, get the array of double elements, double precision values, converted from Java format into native format. And then the integer, Java int, that's fine. That comes across as an integer, so that's good. And then at the end, I'm going to release the native version of the Java array. So this is good. You've got a pair of function calls. Give yourself a native array and then use it and then release it. So in the code in the middle here, I'm going to do some processing on the native array, and then I can return a floating point, and the environment correctly handles that and converts it into Java at the end. So, okay, so that's pretty straightforward. The important thing to notice there really is that there's some processing that goes on when you pass parameters in. So if you're doing this in a way that you're meant to be mindful of performance, then you've got to be aware there is a performance hit going from Java into native if you've got a lot of parameters you're passing over. And so we'll talk about that a bit later when I actually switch over to using the laptop and do some demo stuff. Okay, so I'm trying to work out whether I want to switch over to the laptop at this moment or not. Let's see how it goes. So obviously, if you're going to debug things, I'll talk about debug for a bit. You're going to use -G. So that means generate debug information. Use it in both Java and in the native language stuff. And yeah, I think I'm going to switch over at this point because I think this will be more fun to do live. Well, eventually. So you'll have to kind of bear with me a bit whilst I switch this over. Okay. Let's see how this works. Do you like green? Is there someone at the back who can do colours? That's pretty horrendous. Right. I'm going to assume it's like soft colour in the morning. This will be good on your eyes. My standing up typing is pretty abysmal. Oh, okay, so it's my fault. Sorry. Should have used a bigger hammer. Is it? Okay. I think we're, it's wiring. Right. So, well, it's the switch which probably brings these things out. Anyway, it's looking good now. I don't. It's going to be so weird to be. Okay, I'll try not to move this thing too much. Okay, so I've got a couple of libraries I'm going to compile here. We've talked all about this. You know, CC, debug information, horrendous include paths, and so on. And then I've got a bad Java program. And so I'm going to use DBX, which is part of Studio, to run sorry. What am I doing wrong here? Oh, I know. Oh, of course. Thank you. Oh. When I ran through this late last night, it was all working really tickety-boo, but I'm obviously... Okay, I had to put .class. I remember last night I was working on this and I thought I didn't have to put .class. So anyway, so this is DBX. So what it's doing is it's reading the Java code, and now okay. So now I've told it to stop as soon as it executes the main routine, and then I can run. And here we go. You're going to see a listing of the program as it flashes past. So and then I'm going to step into this. So here's me allocating an array, and then I'm going to go past it. Right, this is running under the debugger, so it's running painfully slowly because the debugger's doing all sorts of nastiness to the Java environment. And so it will take a bit of time for it to iterate only 2,048 elements, which is kind of a bit surprising. And there we go. And so now I can step here. And now I'm into my native code. So this is quite nice. So the first thing to do is to convert the array across. Oh. Okay, and now I'm into my loop. Right, so this is called bad average because it doesn't work, which I should have demonstrated. But the reason it doesn't work is I've got an error in my code, which is I'm passing the wrong value for length in. I'm passing 0 in rather than the actual length of the array. And so I've not actually calculated a total, so when I step out of this, and I'm back into the Java, you can see up here, it printed not a number because it converted 0 divided by 0, and that really doesn't make a lot of sense. So at this point, I know, something went wrong. I can do seamless debugging between my Java code and my native code, which is quite nice. Right. So that's using DBX, and next thing I want to talk about is performance stuff, which is an area I'm much happier in. So I've got here a version of my average code, same thing here going on, and I've got my other Java code which does a bit more work here. It's calling my native code lots and lots of times. And the reason I'm doing that is because this is a demo and I want to actually make it do some work. It's not typical to do that. Anyway, so I'm going to use the performance analyzer, which is again part of the studio, to look at the profile that this generates. Let's see what I need. Okay, so this is why I got confused. I didn't need to put .class this time, whereas in the other one I needed to put .class. And so it's running my little daft test program, and it's producing some sort of result, and that took a few seconds, so we won't have a lot of runtime. A lot of profile data, but we'll have a bit. And so the tool to look at the profile is Analyzer. So I'm going to launch that and see what it's got. So okay. So this is the list of the functions in my application. And what you can see here is there's a whole bunch of Java stuff down at the bottom. And at the top, there's a whole bunch of native stuff. So you should be able to recognize these two function calls, the release double array elements and the get double array elements function calls. And those are the ones we called in order to get the native versions of the Java objects. A whole bunch of mutex stuff. And here's my Java function, and we can look at that. So what I want to point out here is this is obviously where the time is being spent. I'm sorry if you can't quite read the numbers, they're coming up small here. You can see the first column is what we call exclusive time. That's time spent doing the code. And then the second column is what we call inclusive time, and that's time spent calling functions from the code. So you can see that here there's about 11 seconds of time spent calling functions, and that's time spent in the function AV on the native side. And you see this is where we actually call that. So this is the Java code. Now what I can actually do is nip to the disassembly tab, and you can see the Java bytecode. And again here we're calling the function, and that's where all the time goes. And so you can get down to bytecode. Now if I switch to machine mode, if we're lucky, we should be able to switch to the native disassembly for this function. So this is what the Java bytecode gets translated to in x86. So we can go through the entire stack. So I'm going to just go back to here. So that was what the Java side looks like. So I'm now going to look at the native side. So this is my C function. And you can see here that quite a lot of time is spent on the computation of the double array, which isn't that surprising. There's a little bit of time spent on the get and release, which is again interesting. And you can see that what's particularly interesting about that is that there's 0 time spent in the code, but there's 1.5 seconds spent in the processing in the get double array elements. We're going to talk about that in a moment. But the bulk of the time is spent computing the total. So let's have a look at the disassembly for that. And it's here. So here is where all the time is being spent, which is interesting. I don't know how good your x86 disassembly is at this time in the morning, but later on I'm sure you'll recognize this as being x87 code. So the mistake I've made is I compiled this as an x87 library rather than using SSE2. So if I'd used SSE2, I'm sure this would have gone a lot faster. But anyway, you can see that we've looked at Java bytecode, Java source, Java bytecode disassembly. We looked at native C source and native C disassembly. So we're seeing the entire stack. But the other question, so I know where about 8 seconds of my time is spent. There's 11 seconds of time being spent here. So what's going on? Well, the other thing that crops up is memcopy. So memcopy is copying one chunk of memory to another. So why does that crop up? Well, I can look at the call tree here, and you can see that memcopy is called by the get double array elements and by the release double array elements. So let's see what else is called by that. So I'm looking at this in the center here, and you can see that that's my native code at the top calling it. This is the get double array elements function that I'm calling, and it does two things. It calls memcopy and it calls osmalloc. So it's obviously allocating a chunk of memory for the native double precision values. Then it's copying from the Java structure into the native, and if we look at what else goes on here, we can see that when we release it, it's got a mem copy and it's got a free. So this kind of explains why we've got the two function calls there. We've got the get and we've got the release function calls. So what we've got is an alloc call or malloc call and then a free, corresponding free. So that's why we need to make sure we pair them. If we don't pair them, we'll get a memory leak because the memory leaks by malloc and free. And that also suggests why it takes a bit of time. It's because we're now allocating a structure, we're copying into that structure, and then when we're done with that structure, we're copying back out of it and freeing it. So that's where some of the overhead comes in. So you don't want to do too much allocation and deallocation of these structures because they do induce an overhead. Now, something else that goes on here, actually I can probably stick here to show you, OS free. Let's look at OS free. OS free calls free, which is located in libc, as you would expect. So if you have a multi-threaded Java application, you're going to be calling malloc and free whenever you go into the native code. So you will get some malloc activity. And now there's a potential source of serialization because we're now making library calls. And I know on Solaris, the default malloc and free is serializing. So you don't want to do that. You don't want to call too many threads calling malloc and free without replacing the default with something that actually scales. So you've got to be careful here about points of contention. Again, multi-threaded code. So hopefully that, if we want to see why, here's malloc, and it calls a whole bunch of mutex locks that basically ensure that you don't get data corruption when your multiple threads are hitting it. But these are the problem. And by default, we have the libc one, which is not NT hot. There are plenty of replacements on Solaris, but any OS might hit the same issue. Okay. The other thing that's interesting to look at in this tool is the timeline view, which shows basically what's going on here. And we can see that in the detailed view, there's a whole bunch of threads. These are GC threads down here waiting for something to happen. And then up here, we have the application threads doing stuff. So here's the mem copy call where we get the array. Here's the bit of processing, and somewhere along here is probably a free. Okay. So we can actually see over time how the application is working. And that's quite a useful view to have if you have things that are either multi-threaded and you're trying to figure out why they don't scale, or if you're doing excessive GC, you will be able to see at what points in the time view GC occurs. Now, I'm going to try and just finish up from so if I hadn't done the demo, this is the quality of screenshot I managed to grab, which is unfortunately incomprehensible. Okay, so basically I'm stopping at this point because I figure there will be questions, and I figure it's okay to not try and talk for the entire hour. So basically this is covering calling native code from Java. If you do get the opportunity to look at the studio tools, we have the debugger, which does mixed language debugging, and we have the performance profiler, which does, as I demonstrated, profiling of mixed language code. Hopefully those tools will be of use to you. So thank you very much for attending. What questions do you have for me? So. Yeah. That's correct, yeah. it's obviously it's a free download. That doesn't quite answer your licensing question, but I think that might have been your intention. It's available on Solaris for both x86 and SPARC systems, and it also works on various varieties of Linux. Typically Oracle Linux, but also I believe several other variants like Red Hat. I don't know off the top of my head exactly which ones for each release, but it might. And so, if I zip to the front of my talk here, so up at the top here, that's the URL for Solaris Studio. So it's oracle.com, go to Solaris Studio. And you can find out a whole bunch of stuff there, including where to download it. Okay, thanks. Yes, so.
General question, I'm actually Gen A with Gen I.
Okay.
About,
I'm not at the moment, no. No. So my background is more on the native side. So I'm not so worried about how you call it. I'm more concerned about when you get to the native side, making sure you have the appropriate support there to write good code.
so in your example, double,
Yeah.
looks like the entity not.
Yes.
For performance, it's something that's really important to take in variables that are in that position.
Right.
What alternatives are there that
I think it's just the integer types which are efficient. The floating point types, I believe there's subtle differences on that side, so they have to do some degree of conversion. I would just stick, you have to use the variable types you have to use, and when it comes down to it, it's a very similar trade-off to that in many instances, which is everything has a cost, and you just have to figure out how to minimize that cost. So if you are calling native code from Java, and you're seeing a huge conversion cost, then you have to assess what options you got, which are basically, can you hold the values from last time you did this? Or do you actually need to call native code at all? At some point it just becomes more efficient to just do it in Java rather than calling the native code. So I don't think there's an easy way of picking types that happen to not cause you a lot of conversion costs. Because if you're using doubles, that's what you've got to handle.
As your follow-up, can you reallocate a large block of data that you share into the native code that is going to say 1 second, but still be used by Java code? If both of them are pointing to the exact same block,
The mechanism JNI uses is to separate them. So I don't believe that you could. Maybe JNA does something better like that, but I think they've adopted the model for JNI that you have your Java stuff and you have your native stuff, and if you want to go between them, you have to explicitly go between them. I think that sharing a data like that would be kind of nasty. Yes. Possibly. Yeah, I imagine that would be possible. I'm not sure that if you're using the word unsafe, that would be recommended, but possibly. Yeah. I think the reason it's old is that nothing much has changed there. So it still works, and that's quite useful. But yeah, why redocument it? Yeah, it's true. Yeah. Right.
called DLL.
Okay.
How do you get rid of that? DLL becomes overhead.
Anyone want to take that? I don't do Windows. So
You don't see that in Linux or in Solaris, right?
no.
Now, why wouldn't there be an overhead like a lot of native code that supports Java itself, like object creation involves the native code?
Right.
Why doesn't that occur then?
So it would have a slight overhead, but that is part. You're sticking in the Java environment. When you go outside of it, there are costs associated with going to a library, doing the processing that was required. It's like thunking used to be when you went from like 16 to 32-bit. There's a huge amount of horrendous stuff that's takes time. But what I would say to your question is really that you need to find a Windows profiler and take a look and figure out exactly where that cost is coming from. To me, this is the lesson I've learned most of all is that whenever I see a performance problem, I'm like, okay, well, what's causing it? Because the chances are there is something you can do, or at least if you can't do anything, you can at least understand it and maybe work around it. But get a profiler. I suspect the Intel ones would be pretty effective at that. I don't know what their situation is with Java and native, but certainly on the native side, which is ultimately where you're going to be running the code, it might give you more information. Okay. Right. Right. That's an interesting question. We do have a memory checking tool, but I didn't want to determine how well it works with Java. I know that if it looks to me like it would work pretty well for this sort of level of complexity, but I suspect that I would find interesting things out if I tried it on something really complex. But for the native code, yeah, we can do memory checking. We have a very effective memory checker. It won't see the Java code, so it wouldn't understand the Java calls and things, so it wouldn't be able to tell you anything about your Java code. But on the native side, we should be able to do that. I just haven't tried it out myself, so I didn't really want to talk about it today. But yes, I agree. Those are significant problems, and later on today, at Open World, I'll be talking at 10:45 about things like our native memory checker native code memory checker. So yes, significant problem. I share your pain. Anyone else? Right. Yes. Yeah. So Solaris ships I think it's about 5 mallocs for different purposes maybe, or different sort of people's desires. And so it's just a case of LD preloading that, and then all your malloc and free codes will go through it. In fact, that's one of the recommendations I have is, if you're doing native code, don't rely on the default Solaris malloc. Just use like mtmalloc or libumem. Yeah, you can explicitly link at compile time by saying lowercase l and umem or whatever, or you can use LD preload to runtime. So, depends on how you want to set it up. There's one other question. Yeah.
Many years ago, I was called and I had a big performance penalty because it stopped all of while it was running.
Right. Right. Yes, I believe it is still true. I haven't looked into it. When I was discussing this with one of my colleagues on Friday, he said, yeah, you're going to get questions about garbage collection and JNI. And, you know, as far as he knew, that things hadn't evolved much in that space because it's a complex problem, I think was the overall feeling. So, yeah, I don't know that it has changed that much. Okay. Anyone else have questions this morning? Not to my knowledge, no. I don't think I have an exhaustive knowledge of them, but I haven't observed any about JNI. The ones that I've played with most are about garbage collections, get the verbose details of that. Because that seems to be the big area when you hit a performance problem is, what does the GC look like? Okay. Well, thank you all very much for coming out early this morning.